Yes.
Good morning and welcome everyone. I Prajwal welcome you all on the behalf of GH Raisuni Institute of Engineering and Business Management Jalgaon to this faculty development program on security aspects of blockchain technology, day 5 by Dr. Bodhisatwa Mazumdar sir. Sir has done his PhD in Computer Science and Engineering from IIT Kharagpur 2015, MS Electronics and Electrical Communication Engineering from IIT Kharagpur in 2009. Sir is currently working as Assistant Professor in Indian Institute of Technology, Indore from March 2017. Sir has also worked as postdoctoral associate DFX Laboratory, New York University, Abu Dhabi from July 2014 to February 2017. Sir was also a member of Technical Staff Manthan Semiconductors Private Limited, Bangalore from 2008 to 2009. Sir has also worked as hardware design engineer in Wipro GE Healthcare Private Limited, Bangalore from 2007 to 2008. In research and interest, Sir has his special hand in hardware security, side channel attacks, cryptographic implementations with improved resilience against side channel attacks, logic synthesis techniques for hardware security. Awards and honors: Best Research Paper Award at 25th IEEE International Conference on VLSI Design, Hyderabad 2012. Sir was also nominated for the Best Research Paper Award at IEEE International Symposium on Hardware-Oriented Security and Trust 2013, Austin, Texas, USA. Program Chair for Cyber Security Awareness Week Research Competition at New York University, Abu Dhabi in 2016. Technical Program Committee Member, IEEE VLSI Design and Test from IIT Roorkee, India. Sir has also worked in participated in 7th International Conferences on Security, Privacy, and Applied Cryptographic Engineering, Space 2017, Goa, from 15 to 17 December 2017. Now, without taking much of your time, passing the control to you, sir.
Okay, thank you for the wonderful introduction. Just a small correction: the designation should be associate professor, not an assistant professor. So earlier I was an assistant professor, now I am an associate professor. So I'll just share the slide. I hope this slide is visible.
Yes, sir.
Okay. So good morning, everybody. So welcome on security aspects in blockchain technology. So when we talk about the blockchain technology, what do we exactly mean about the blockchain technology? Okay, so with traditional methods for recording transactions and for tracking the assets, participants participants on a network, what they do is that they keep their own ledger, okay, and other records, okay. Those records can be in the form of documents and so on and so forth. So conventionally, this method could be expensive, okay, and why? Because it partially involves the intermediaries. In many cases, it involves intermediaries, and hence a significant amount of fee is always associated with it over a period of time. Okay, so and also in addition, it is clearly inefficient due to the delays in executing the agreements, and there occurs the duplication of the effort that is required to maintain numerous copies of the ledgers. Okay, and in addition, such architectures are also vulnerable because if a central system, for example, a bank, if you consider a bank, okay, it can be compromised due to certain frauds, cyber attacks, or even by a simple mistake by a bank employee. Okay, and it can affect the entire business network. So in such a scenario, a blockchain architecture, what does it do? It gives participants the ability to share a ledger. A ledger is nothing but a record, okay, and that ledger is updated through a peer-to-peer interaction. Okay, and each time a transaction occurs. So for instance, this transaction could be in the form of a financial transaction. This transaction could be in the form of a record transaction. Okay, we'll see an example. Okay, through a car manufacturing industry. Okay, how a blockchain technology could be implemented. So before going to the security aspects of blockchain technology, first we go to the blockchain basics. So ledger, okay, that is cryptographically secured. That means its security. That means the security of the data is established through cryptographic mechanisms, and such a ledger is basically append only. That means once you have put a data into that ledger, that is this record, you cannot delete that data. Okay, for instance, if you have made an incorrect financial transactions, okay, then to correct it, you need to make another set of financial transactions. Okay, so it is an append only record. That means you can only add transactions to this record. Okay, you cannot delete any transaction, and it is immutable. That means once you have entered a transaction into this ledger, okay, you cannot modify it. And if you have to update or if you want to add any record to this ledger, okay, this updation has to be done through a set of consensus or agreement among the peers. Okay, so this is an example of a blockchain in the car manufacturing industry. So over here we have different nodes in the car industry. The first node is that of a regulator or the manufacturer who manufactures the car. So this manufacturer, for instance, in case of Maruti, this car is manufactured somewhere in Haryana. Okay, and from that place, okay, those Maruti cars, okay, they are being sent all over the country. So after the manufacturer, the next node comes to the dealer. That means the cars come to the dealers. Okay, so the dealer has to process a certain set of transactions. Okay, and these transactions, these records, okay, whatever rules, okay, that are need to be taken care of, those rules are written in the smart contracts. That is, over here in smart contracts, all the conditions for any type of asset transfer. So in this case, the asset is basically a car, a new car. So whenever a car is transferred from the manufacturer side to the dealer side, okay, a certain set of rules or conditions have to be satisfied. Okay, and they are written in the smart contracts. And whatever transactions that are being processed, they are being added onto this. It holds the records for asset transfer. So each of these assets, that is each car, okay, will have its own record. And when that car passes through different nodes, for instance, from manufacturer to the dealer, from dealer to the leasing company, from leasing company, so suppose leasing company, it gives the car, okay, to different lessees, okay, to different customers. So the customers will drive that respective car and will return to the leasing company after a certain period of time. Okay, and after the car has been used for a certain number of years, say for 12 years or 15 years, then that car will be sold to the scrap merchant. So altogether we have 5 nodes over here. First is the manufacturer, then we have the dealer, the leasing company, the lessee, and the lessee is the user, and then from the lessee, the car can be handed to the scrap merchant. So whenever this car is being transferred from one node to another node, okay, a particular set of smart contracts that needs to be executed, that is the rules or conditions need to be satisfied, and if the set of conditions satisfied, then the corresponding transfer is recorded onto this shared ledger. So this shared ledger is nothing but the blockchain. So now when we are considering this ledger has to be shared between all the nodes, that is the manufacturer, the dealer, the leasing company, the lessee, and the scrap merchant. So what do they do is that they keep a record of the shared ledger at each of their nodes. So whenever the shared ledger gets updated, okay, the same update should happen at each of these nodes at the same time. That means what? That means in this case, the synchronism is basically very important. So how do you update this ledger? It has to be through a set of consensus or agreement schemes. So now what does a blockchain do? So as we see, this blockchain or the shared ledger mechanism, it facilitates the process of recording the transactions and tracking the asset. That means which set of cars at a particular instant of time are with the leasing company, which set of cars are with the lessee. Okay, so the leasing company can track, okay, that which cars are with a specific lessee, okay, or how many lessees are being assigned the respective cars. So all those things okay, that is the tracking assets in a business network can be done through this blockchain mechanism. So now when we are talking about asset, what is an asset? Assets usually come from in two forms. First is the tangible asset. That means what? That means in tangible asset, the asset usually have a physical entity. For instance, house, car, cash, or land. Or an asset can be intangible. That means it may not have any physical existence, but it has a monetary value associated with it. For instance, intellectual properties, patents, copyrights, and branding. So assets can be in either of these forms. It is tangible asset and intangible asset. Now, anything that has a monetary value or a financial value associated with it can be tracked and traded on a blockchain network. That means at specific instances of time, okay, how did the asset move from one entity to the another entity? For instance, in case of a car, okay, when a car moved from the manufacturer to the dealer, and then from the dealer to the different lessees, okay. Instead, okay, certain validity checks need to be done. For instance, whether the user has enough balance buy a certain commodity, okay, and when he tries to buy a certain commodity, he needs to pay, and for paying a certain specific amount, okay, a check needs to be performed that whether that user has a sufficient balance or not. So whenever a user requests a particular transaction, that validity of this transaction is established by different nodes. Okay, so the requested transaction is broadcasted on a peer-to-peer consisting of the computers, and these computers are known as nodes. So this network of nodes, it validates a set of transactions. So at the same time, multiple users, okay, on this network may be requesting transactions. So this network of nodes, they establish the validity of the different transactions. Okay, and once majority of the nodes establish the validity of a particular transaction, then this transaction is validated, and then it is put onto this blockchain record. Okay, that is onto this ledger. Okay, so in this case, a new block is created. So whenever a particular set of transactions get validated, then a new block is created, and all those transactions within that particular time window, they are put into that block. So now the question is, why blockchain? Why do we need a blockchain? Blockchain is required because it provides an efficient, cost-effective, reliable, and a secure system for conducting and recording the different financial transactions. So when we talk about the present transaction system, the most primitive form of a transaction system is cash. And cash is, we have found it is useful only in local transactions, and that too in relatively small amounts, okay, because we need to count the cash. Whenever there is a cash transaction, we need to count the cash, okay, and this is only possible when the transaction amount value is significantly small, okay, and usually the present transaction system, in certain cases, it may take a long time between a transaction, once a transaction is performed and the settlement is being done, okay, and there often requires a need for a third-party validation, okay, or the presence of intermediaries that will lead to the inefficiencies. Okay, for instance, in many cases, okay, a certain amount may be debited from your account, okay, but that amount may not be transferred to the recipient's account. Okay, so in that case, okay, you have a time delay of say 1 week or 2 weeks for the amount to get back to your account. So whenever there is a scenario of a third-party validation or intermediaries, it occasionally leads to inefficiencies. And moreover, we have seen over the past decade, there have been numerous frauds, cyber attacks, and even simple mistakes by the employees of the bank, okay, that jeopardizes the entire business network. So central system such as a bank, okay, that may get compromised in the event of such threats. And there is occasionally limited transparency and inconsistency, okay, for the information, okay, to to go from one place or to be shared between multiple entities within a specific industry. And we have been seeing that the business volumes, the transaction volumes worldwide are growing exponentially, okay? And that has led to an emergence of increased complexities, vulnerabilities, and inefficiencies, okay? So having said that, the primitive role of a blockchain is that it helps in building the trust between the different nodes or the different entities, okay, which are involved in such transactions. So these are the different these are the different features that are being given by the blockchain, a typical blockchain system. Okay, so blockchain enhances the trust across a business network. Okay, so and it is particularly valuable at increasing the level of trust among the network participants, as I said. So these are certain aspects or characteristics of a typical blockchain network. So the first is the distributed and the sustainable feature. What do we mean by the distributed and the sustainable feature? So over here, the ledger or the record that I was talking about, the ledger is shared and it is updated with every transaction, and it is selectively replicated among the participants, between the participants in almost real time. So there is a very minimal delay in the updating of the records. And as it is not owned or controlled by any single central entity, for instance, there is no banking system over here. Okay, so there is no single central entity. That means the blockchain platform's continued existence is not dependent on any individual entity. Okay, if a certain central entity crashes, okay, then the system will not fail. Okay, so that imparts the sustainability feature over here. Then the next part is that of security. That is a secure, private, and indelible. So what does it mean? It means different permissions for performing a transactions, and cryptography. In this case, it prevents unauthorized access to the network. Okay, and it ensures that the participants are indeed the members who they claim to be. And so we have different aspects of security and privacy. For instance, confidentiality. So the confidentiality of the transactions, it can be maintained through cryptographic techniques or data partitioning techniques that gives the participants, okay, a selective visibility into the ledger. That means a participant may not be able to see, okay, the transactions that happen for another user. Okay, so a selective visibility can also be imparted. Okay, and both the transactions and the identity of the transacting parties, that they can be masked as well. Okay, so there are algorithms that provides this thing. And when the conditions are agreed to, the participants cannot tamper with a specific record. Okay, so whenever a record gets put into the ledger, okay, nobody can modify that record. So errors can only be reversed with new transactions. So if you have committed an error in performing a financial transaction, you need to perform another transaction to negate that error. So this imparts the feature of security, private, and indelible. Then the next characteristic is that of transparency and auditable. So as the participants in a transaction have access to the same set of records, they can validate the transactions and they can verify the identities or ownership without the need for third-party intermediaries. So over here, the transactions, so whenever the transactions within a particular time period are being made, they're basically time-stamped and they're basically ordered and they can be verified in real time. Okay, so there is a very minimal delay in establishing the validity of the transaction. So that's why it's called transparent and auditable. Participants, they must agree, okay, that each blockchain network can establish the conditions, and those conditions will be required, and asset exchange can occur. For instance, we have seen how a car moves from the manufacturer side to the dealer side, and from the dealer side to the process with a wide range of activities. Okay, so now when we are talking about building the trust with the blockchain, so what functionalities impart this trust? So we have primitives. So to start, applications of cryptography has there is a sender and the receiver.
So your voice is not audible.
Hello?
Yes, sir.
Am I audible? Am I audible?
Yes, sir.
Hello? Okay. So when we're talking about the cryptographic background, so in communication we have this aspect, that is the confidentiality, integrity, and the authenticity. Okay. So when you're talking about the confidentiality means whenever there is a sender and the receiver communicating the messages should be intelligible only to the sender and the receiver, and no eavesdropper who is snooping onto this communication link. Okay, he should
So
not be able.
presentation is also not visible.
I had shared it. Not visible? Is it visible now?
Yes, sir.
Hello?
Yes, sir. Yes, sir.
Okay. So when you're talking about this communication, okay, so from the communication perspective, the cryptographic primitives, it provides these features of confidentiality, integrity, and authenticity. Okay, and from the computation, that is the data computation. Okay, cryptographic primitives, they provide the privacy property and the correctness, and they help in establishing the correctness of data and the programs, even without knowing the data. Okay, whether the data computation of the data is correct or not, or whether the programs are correctly executing or not. Okay, this correctness of these processes, they can be established through a set of cryptographic primitives. So for this, we have different types of cryptographic primitives. For instance, pseudo-randomness, that is the pseudo-random number generators. We have different protocols that are based on the probabilistic proof verification. Okay, and we can establish the average case or the worst case hardness. Okay, for mounting an attack on such primitives. Okay, so they are being established through different mathematical tools, from number theory, elliptic curve theory, coding theory, and combinatorics. So cryptography gained specific importance from the year 1976 onward, when the public key encryption it came into the picture. So when we talk about the public key encryption, what we do is that in this case, okay, the sender and the receiver can exchange secret messages without ever meeting. That means in public key encryption, okay, we have a set of public key as well as a private key. Okay, so this encryption or decryption, the encryption happens through the public key, and the decryption at the receiver's end happens through the private key. And then we have the digital signatures. So in digital signatures can be used to sign the contracts remotely. So whenever we have the new smart contracts that are coming up, they could be signed by the entity or by all the entities, with the help of the digital signatures. And then the pseudo-random number generation, it can be used to generate primitives, that need to be indistinguishable from the random generators. Then we have protocols for zero-knowledge proofs. So in zero-knowledge proofs, they establish the proofs without revealing any information about the data. So you can use the zero-knowledge proofs to establish that, that this data, whatever computation that is happening over the data, that is indeed correct, without revealing any information about the data. So zero-knowledge proofs, can find a use in that. Then we have two-party secure computation. For instance, say suppose there are two parties, party 1 and party 2, and a specific computation needs to be split between both the parties. Now, the condition may be that both the parties, don't trust each other. That means they don't want to exchange information with each other. So how can such a computation? We have primitives that exhibit this property called the two-party secure computation. And then we have multi-party secure protocols as well. So it helps in computing on distributed secret data that reveals nothing but the result without the reference. So coming to the public key system. So when we have a public key system, that is a public key encryption, we have a pair of keys, as I said. So there's a public key PK and a secret and a private key or the secret key SK. So the public key of a user that is widely disseminated, through a database management system, and there's a private key that is kept secret with the user. So this private key is only with the user, and nobody else in the network knows this private key of that respective user. So each user will have his or her own private key, that is not known to any other user in the network. And the public key of that user will be shared with all other users. So the private key is used by the party who generated it, and public key is used by everyone else. So as we have two different keys, so this mechanism is called the asymmetric key cryptography. And over here, the security must hold even if the attacker, so this is the security assumption, that if the attacker knows the public key, of this mechanism, even then the security should hold. So this is a public key distribution model. So in this case, you have PK as the public key of the user and SK is the secret key of this user. So what she does is that she uploads her public key to the public information database. So any other entity or any other user who wishes to communicate with this person, he first need to access the public key of this recipient, and then he will encrypt that message with the public key of the of this recipient and send it to the recipient. This is another model. Instead of a public information database, the recipient can directly send the public key to this user. So why a public key encryption is required? It addresses certain drawbacks of the private key encryption, and the drawbacks of private key encryption are as follows. First is the key distribution. So in a private key encryption, what happens is that both the sender and the receiver, they operate on the same key. So whenever the sender and the receiver, they work on the same key, then a problem comes, how can we share the same key between the sender and the receiver? That is, this leads to a key distribution problem. So public keys can be distributed over the public, but authenticated channels, but the private key, we cannot distribute them. So key management in large systems of n users, so each user stores one private key and that user gets access to n-1 public keys. So these public keys can be stored in central directory, and it has found applicability in the open system, certain open systems. But despite that, why do we need to study private key cryptography? The private key cryptography is also finds its use in certain applications, for instance, disk encryption, or when the security measure is not that high. Actually, private key cryptography is much faster than the public key cryptography. So if you have an option for using the private key cryptography, then you should certainly use it because it is much faster. But if the security requirements are much higher, then you need to go for public key cryptography. But the public key cryptography, it is roughly 2 to 3 orders magnitude slower than the private key cryptography. So this is the public key encryption that I was talking about. So this user wants to send an encrypted message. So what he does is that he accesses the public key of this recipient from the database. He accesses that public key, and then what he does is that he generates a message. So this message could be a set of files, okay, or even a single file. And what he does is that he encrypts this message with the public key of the recipient. So this is the encryption operation, and after encryption operation, you generate the ciphertext, and this ciphertext is sent over this communication link to the recipient. Now the recipient, after receiving the ciphertext, that is the C ciphertext file, she decrypts this ciphertext file with her own secret key. So now this secret key is not known to anybody else. So after decryption, she recovers back the original file. That is, original file is M over here. Over here, this is the original file, okay? And now you have the original file over here. So she recovers the original file back after decryption. Okay, so the public encryption. So for any public encryption scheme, okay, it must satisfy this correctness property. That means if a message M, if it is encrypted through a public key PK, and after encryption, when the encrypted text is decrypted with the corresponding secret key, then we should get the message back. And this property should be true for all messages, for all public key, and for all corresponding secret keys that are being output by the key generation function. Okay, so public key encryption, it provides for the CPA security, that is a chosen plain text attack security. So in this chosen plain text attack security, so this is the formal model of this chosen plain text attack security. In this case, okay, you run a randomized algorithm. So the randomized algorithm, it takes in a parameter that is the size of the key. So this is the size of the key, and this randomized algorithm, it generates a pair of keys, that is the public key and the secret key. Then this public key is given to an adversary who outputs two messages, M0 and M1 of the same length. Okay, and she randomly chooses one of these messages. So if B is equal to 0, then the adversary chooses M0. If B equal to 1, the adversary chooses M1. Okay, and he asks an oracle to encrypt, okay, this message, this MB message, okay, to generate the ciphertext C. Now the adversary's role is to guess that this ciphertext that he has obtained, this ciphertext is generated by which message, whether this ciphertext came from M0 or whether this ciphertext came from M1. So if the adversary's guess, that is B dash is equal to B, then that means the adversary has been successful. Okay, and if B dash is not equal to B, then the adversary has failed in identifying what is the message. Any questions until this point? Anybody? Any questions? Okay, so the probability of success of an adversary in this public key cryptography, that is the CPA on this public key encryption, okay, this should be very, very close to half. Okay, so there should be a very negligible increment in half. Okay, so this is what we call as the success measure of an adversary. So the success measure of an adversary should be very, very close to half. So now, in this case, what we do is that we are using this public key cryptography, okay, to share the key as well as to send the ciphertext. So what we are doing is that this key PK. So now we have the symmetric key cryptography. Over here, this key is used to actually encrypt the message. And as well as this key, the secret key, is encrypted with the public key of the recipient. Okay, so you have performed the encryption. So now this key is encrypted. So now this is the encrypted key, and this is the encrypted message. So now when the recipient receives this ciphertext as well as this encapsulated key, he or she should first decrypt this encapsulated key with her own secret key to get this key back, and then use this key to decrypt this ciphertext. So this is the functionality of a public key encryption scheme, okay, that has an efficiency of the private key encryption scheme. Okay, so this is the security of the hybrid encryption. So let pi be the public key component and pi dash be the private key component. Then pi hybrid denotes their combination. So this is how we establish the security of an hybrid encryption. So now the first function is that of an authentication. For instance, this is an example. For instance, over here, there is this person Bob who buys, say, suppose a book on a network, for instance, say on Amazon. So this person, he or she buys a book from Lisa on Amazon. So now what he does is that first, in the process of buying, first he needs to make a payment. So she pays this $10, okay, to Lisa. So Bob pays $10 to Lisa, and when he is sending this message, okay, he needs to encrypt this message with his with his own public key. Okay, so he signs with Bob signs with his own private key, and when it signs with his own public key, the corresponding verification of that signature is done by Lisa with the Bob's public key. So this is authenticated by the Bob's public key. So in this way, the Bob is sending money to Lisa to buy an ebook. Okay, and then after Lisa validates this transaction, she provides a link to the ebook to Bob. And this link is basically signed by Lisa, okay, and this is signed by Bob's public key. So she signs it with the Bob's public key so that Bob can decrypt it back with his own private key. And after decrypting, he recovers this original link. So after receiving the payment, Lisa sends that link of the ebook to Bob. So this is the case of message privacy, and the first one is the case of message authentication, that whether the message is coming from the correct person or not. Any questions? Anybody? Okay, we're talking about the hash functions. It is the cryptographic hash functions that are used in the typical blockchain technology. So this hashing mechanism, in this case, so whenever you are performing a transaction, for instance, suppose you are buying a commodity, okay, over a blockchain platform, then this basically, in this case, this transaction has different components. For instance, whenever you are putting out a transaction, you need to sign that transaction record. Okay, you need to sign with your own private key. Okay, and this private key, it needs to be verified by the another party who is involved in the transaction. So owner's one's public key is used to validate the owner zero's signature. Okay, and this basically flows over the network. So over here, in this transaction, okay, so owner one has signed with his own private key. So what he has signed the hash value of the owner one's public key and the document that needs to be signed. So this is passed through a hash function, and this hash function is signed with the private key. Okay, then this transaction would be validated with the owner's one public key. By the owner's one public key, with the owner's one public key, you will verify that document. So this is how the transfer of currency transactions happen over a blockchain technology. So in this case, we have different cryptographic primitives, that is the hash function over here. So what are the typical properties of the hash function that we will come to know, and how this, and what are the requirements for this digital signature. So now when we're talking about the hash function, what is the hash function? A hash function basically, it takes a string of any size. So that size could be of any length. Okay, it could be even order of gigabytes, it could be order of terabytes, okay, of any length. But this hash function, it always produces a fixed size output. For blockchain, it is typically 256 bits. Okay, and moreover, this hash function is efficiently computable. So what does efficiently computable means? It means that the hash function should compute the entire computation, which should be linear in terms of size of the input. Okay, it should not be of exponential order. Otherwise, your hashing function may not finish, okay, within a finite time. Okay, if the size of the string is very large. So in addition to these characteristics, there are certain security properties that hash function should satisfy. The first is that of the deterministic, that is the hash function should be deterministic in nature. It should be collision resistant, and it should exhibit the hiding property. It should also exhibit the property of buzzer friendliness, and whenever you are making a small change in the input value, okay, it should randomly change the hash value. Okay, so that is from the hash value, you should not be able to find out the input. That means it has to be a one-way function. So the first property of a hash function is that it has to be deterministic. So what is meant by deterministic? It means that every time you give the same input to the hash, it must generate the fixed hash. Okay, it should not be the case that if you are providing the same input at over multiple times, okay, and for the same input, the output changes each time in each iteration. So that should not happen. So if for the same input, if the output is also the same, that means the hash function exhibits a deterministic property. So what happens if this property is not really present? If the hash function, if it is not deterministic, then the reliability of the entire technology that goes haywire. Nobody would rely. Okay. The second property of the cryptographic hash function is that it should be collision resistant. What is meant by collision resistant? It means that for two different inputs, say x and y to the hash function, okay, the probability of finding the same output, it should be negligibly small. That means nobody can find x and y such that if x is not equal to y, then h of x is equal to h of y. That means nobody should be able to compute two different values of x and y which collides to the same value. That means which outputs the same value, for both of which the output is the same. Okay, so finding two such different inputs, it should not be possible for any adversary. Okay, so this property is called the collision resistance. That is, for x not equal to y, the output should be always false. Okay, even though the actual output is true, that means even though the collisions exist, okay, nobody should be able to find. That means it should be computationally infeasible over a period of time. Then the next property is that of collision resistant. As I said, in that case, as I said, the hash function, it takes inputs of very large size. So the input can be of very large size. That means the domain of the values that it comes from, that domain size is very large. Whereas the output is a fixed size. So as the output is always a fixed size, that means the domain or the range of values of the output is very small. So when you are mapping, so hash function is what? It is basically a function. That means it maps from this domain to this domain. So this domain is a very large domain. That means these collisions will always exist. But if your output space is very high, that means if it's a 256, even though it is fixed, if it is 256, that means the output sample space is 1 by 2 raised to the power of 256. That means the probability of finding a collision, that is negligibly small. Okay, so typically it should be very hard to find a collision, but there are certain attacks such as the birthday paradox, okay, which significantly reduces the sample space, in which you can improve your probability of finding a collision. So this is the birthday paradox. I'm not going into the technical details, okay, but it has until now has been the fastest tool to find the collision, to break the hash functions. Okay, so for cryptographically strong hash function, if you know hx equal to hy, it is safe to assume that the respective inputs are same, that is x is equal to y. So to recognize a large file that we saw earlier, we just need to remember its hash. So this hash function could be used for proper storage of the files. Okay, and it is useful because the hash size is itself very small. The third property of cryptographic hash function that is used in a blockchain technology is that of a pre-image resistance. So what do you mean by pre-image resistance? It says that given h of x, it should be impossible to find x. That means what? That means over here, the input sample space should be very large. For instance, if you're tossing a coin, okay, this tossing of coin can have two results, either heads and tails. Now, if you pass this head through a hash function and if you pass through tails through a hash function, so obviously these two hash values will be different. So right from observing the hash values, you could identify what was the result of this coin tossing experiment. So as the sample space is itself very small, so from the hash values, you could easily identify what was the corresponding input. That means what? That means your experiments should not have a small sample space. The sample space should be very high. That means it should be computationally infeasible to mount an exhaustive search attack on the entire input space. Okay, so X should be chosen from a set of values which is large and must be spread out. So for an adversary, it should not be able to try all possible values of X. That means he should not be able to mount an exhaustive search attack on the entire sample space. And he should not be able to find few but high probable values of X. If the values of X, if they are not uniform, if certain values of X have a very high probability of occurrence, then even in that case, you should not be able to successfully mount an attack. So this property, pre-image resistance, it guarantees resilience against such attacks. Okay, so this leads to the hiding property in the blockchain technology. That means what happens in the blockchain technology is that a random value R, so probably this R is generated from a pseudo-random number generator. So if R is chosen from a probability distribution that has a very high mean entropy. What is meant by a high mean entropy? High mean entropy means you have a very large sample space. Okay, you have a very large sample space and the probability of occurrence of each sample is very small. So in that event, we say that the probability distribution is coming from a very high mean entropy. Then what do you do is that suppose this is a user input. Occasionally the user input may not be random, because say suppose X could be a financial transaction or a certain monetary value that the user wants to perform. So this X may not be random, but what is being done is that with X you append a random value. So this R is coming from a probability distribution with a high mean entropy, and it is specifically generated from a pseudo-random generator. So this R is appended with X, and this entire input is passed through the hash function. So now, if an attacker, if he or she observes the output of the hash function, by observing the output of this hash function, he or she should not be able to find or get any information about X. So this property, this security property is called the hiding or even pre-image resistance. That means even after observing the output of the hash function, the attacker should not be able to get any information about X. It should be infeasible to compute X. Okay, so high mean entropy means that this distribution is very spread out, so that no particular value is chosen with more than a negligible probability. For instance, the probability would be 1 over 2 raised to the power of 256. That is a very negligible probability. That means you cannot guess at a particular time instance or at a particular iteration which input value was chosen. Okay, so for a hash function, any particular string R is chosen with a probability such as 1 over 2 raised to the power of 256, which is indeed a very negligible value. So this is an analogy of the hiding property. So in this case, what you do is that you seal a value in an envelope. So suppose you seal you put a note, okay, into an envelope and you seal the envelope. Okay, and at a later point of time, okay, you open the envelope and take out that note, okay, to check whether indeed that money is safe or not, or whether the claimed amount that is say I have put 10 rupees or 100 rupees in that envelope, that could be established. So putting that money into that envelope is called committing to a value, and then later on it is revealed or verified. So first is the commit mechanism. So commit means putting that message or that fees or that monetary value into that envelope, and that is being done with the help of a key to generate the COM. So over here, the COM is basically the envelope. Now, at a later time, okay, this COM or the envelope is opened with the key to find the actual message. That is, whether the claimed message is the same as a message that is there in the envelope. If it is so, then we declare it is a match. So this is the act of sealing the message in an envelope, and the other one, that is a verification, is the act of opening the envelope to see the message. So this is a typical application of the hiding property or the commitment API. Okay, so this commitment scheme, it consists of two schemes. First is the commit scheme, as I said, and the second one is a verify scheme to establish that whether indeed the claimed amount is indeed correct or not. So it needs two security properties to hold. The first is the hiding property, that is given the COM, that is even after looking the envelope, okay, you should not be able to tell what amount of money is there in the envelope. That means, given the com, that is the encrypted value, it is infeasible to find the message. That is what is being stored within the envelope. And then the other property is that so the first property is that of hiding. The second property is that of binding. So in binding, it is infeasible to find two pairs. That is, if you have two pairs, say message and the corresponding nonce. What is nonce? Nonce means number used once. Okay. So if there are two pairs, say message and nonce and message dash and nonce. Okay. If this, even though this occurs, you should not be able to find two such pairs such that message is not equal to message dash. That means the commit value of two different messages should not be same. Okay, even if it is same, okay, it should be infeasible to find two such message pairs, different message pairs. So this property is called the binding property. Am I clear with this? Any questions? Any questions from the audience? Okay. So now there are certain rules. That is, every time you commit to a value, it is important that you choose a new random value nonce. So over here, nonce is basically the random value. Okay, so in the hiding property, whenever you are storing a certain value, say x, you need to append x with a random value, and that random value is nothing but this nonce. So this nonce is generated from a pseudo random generator. So the security properties are hiding, and the second security property is the binding. So it should be infeasible to find two different messages, okay, such that when you commit with one message and if you verify the same commitment with the another message, okay, this leads to true. So this should not happen. For two different messages, okay, this with the verification should not give you true. If it exists, that means the security property, that a binding property is getting violated. That means such a hash function, such a mechanism could be easily broken. So these are the certain security properties that needs to be guaranteed while using a typical hash function or constructing a typical hash function. So what we see over here is that when you are using a cryptographic hash function, whenever we have a message, for instance, the message is nothing but the financial transaction value. So along with the financial transaction value, you are appending that with a random number, that is a nonce. Okay, so nonce is basically a random 256-bit value, and this entire data is passed through the hash function. So the output of this hash is basically the commit value, and then you take this commit value, okay, and then you check that whether this is indeed the commit value that you have already committed earlier. Okay, so these are the security properties. First, given the hash, you should not be able to compute the message, and for two different messages, that is message and message dash, okay, the corresponding hash values should not be same. That is, it should exhibit the property of collision resistance. The next property of such hash function, this cryptographic hash functions, is that of puzzle friendliness. So what is puzzle friendliness? So this property of puzzle friendliness required for the cryptographic hash function is typically required for blockchain technology. So in this case, what happens is that what is meant by puzzle friendliness? In this case, for every possible n-bit output value. So suppose you are given the output of this hash function. Okay, so the output of this hash function is say y. So if for every possible n-bit output value, if k is chosen from a distribution with high mean entropy, that means if k is randomly chosen, and when this k is appended with x, that is the user input, okay, then by observing the y, if an attacker is given this value of y, that is the hash output, the attacker should not be able to get any information about this user input x. Okay, so it should be infeasible to find x such that the hashed value of this leads to y in a polynomial time, that is a time significantly less than 2 raised to the power of n. So 2 raised to the power of n is basically an exponential time. So a search puzzle, so over here, when we talk about a puzzle friendliness, that means there exists a search puzzle. So what does a search puzzle consist of? It comprises of a hash function. It comprises of the puzzle ID, and this puzzle ID is chosen from a high mean entropy distribution. That means the probability of selecting a particular ID value should be negligibly small, and there should be a target set y. So this hashed output y, it comes from this target set uppercase y. So a solution to this puzzle is basically a value x, such that when this x is appended with this random value ID, okay, that is a puzzle ID, and when this is passed through this hash function, it belongs to this target set. Okay, so gradually what happens over a period of time, okay, the probability of finding such an x, it decreases over time. Any questions? Anybody? Okay, so over here, okay, so what we are discussing the typical cryptographic properties that should be exhibited by the hash functions in the blockchain technology. Okay, so this hash function, it provides the services of data integrity. It can be also used to impart the authentication as well. Okay, so the last property of a hash function is that even if you make a very small change in the input, that should change the output, hash output, that is the hashed value, drastically. So this ensures the greatest quality of the blockchain platform, that is the immutability. That means a tamper-proof ledger. That means any data when it is entered into a blockchain, that data in any case will not be modified. If it is modified, it will be easily detected. So over here, what we see is that, so suppose this is the input. So these are two inputs. This is a test. This is a test. The only difference between those two input strings is the first letter of this string. So the first letter in the first example is uppercase T. In the second case, okay, the T is lowercase. So even for this very small change, what we are seeing is that this output hash value, it has changed randomly. Okay, that is, by observing the hash value, you cannot say this hash value came from this is a test, or whether this came from this input. So this is called the so this refers to the fifth property of this cryptographic hash function. So it imparts the property of immutability to a blockchain framework. So the standard function that we use is basically the SHA-256. So why 256? Because it uses an IV of 256 bit. So what we see is that this entire message, so this message could be of any size. So what is being done is that this single large message is split into multiple blocks, block 1, block 2, up to block n, such that each block has a size of 512 bits. Now this 512 bits message is passed on along with the initialization vector, that is of 256 bits, and this is passed through a compression function C. So this compression function C, it generates a 256 bit output, and then this output is again appended with the next message block and is passed on along to the same compression function, and it is being done multiple times. Okay, and at the end we get a 256 bit hash output. Okay, so this is all about the hash functions. So typically when we implement a hash function in a blockchain technology, we use hash pointers and that address corresponding data structures. So over here, what is a hash pointer? So a hash pointer is nothing but, it is a pointer that points to the data. So what is a pointer? Pointer is basically an address value that points to the location where the data is stored. That is, pointer is nothing but an address. It points to the address where the data is stored. So a hash pointer is nothing but, along with that address value or the pointer, it stores the hash of this entire data. Okay, so this is referred to as the hash pointer. So whenever this data gets changed, okay, then the modified data will have a different hash. So whenever a data is stored into the memory, okay, it is addressed to a hash through a hash pointer. So it ensures the data integrity check for this location. Okay, so a hash pointer is a pointer to where data is stored together with the cryptographic hash of the value of that data at some fixed point of time. So a hash pointer also gives us a way to verify that the information has not changed. Okay, and we can use pointer-based data structures such as a linked list or a binary search tree. So we usually use a binary search tree over a linked list. Why do we use a binary search tree over a linked list? Anybody?
चांदणी पण यायला चांदणी 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 म्हणा चांदणी म्हणजे
When can we use a binary search tree? A binary search tree basically it minimizes the searching time. Okay, so the searching time. So if you have a record of, say, if you have n records in the list, so the searching time on a binary search tree would be of the order of log n, whereas in a linked list it is of the order of n, which is a linear time. So binary search tree, the searching time in a binary search tree is significantly small. So we can use pointer-based data structures such as linked list or binary search tree, okay, and implement it with the hash pointers instead of the pointers as we normally do. So this hash pointer, it provides the guarantee of tamper-proof property. So it exhibits the tamper-proof of this memory. So in this case, the blockchain is implemented as a linked list. So over here, this is for this data. This data is pointed to by this hash pointer. So whenever there is a change in this data, okay, the corresponding hash value needs to be changed by the attacker, okay, to escape the detection. Okay, so whenever a data is changed over here, then when you pass this data through the hash function, that hashed value and this hash value will not match. Okay, so it will be easily detected. So this provides a tamper-proof property of the blockchain. So to escape that thing, okay, the attacker, if he needs to change this, modify this data, he needs to modify this hash value as well. And when he changes this hash value, that means it changes this data as well. Again, to escape the detection, he needs to change the corresponding hash value over here. Okay, so he needs to modify multiple data blocks. In order to modify a single data block, he needs to modify all the previous data blocks. Okay, so this imparts the tamper-proof property of this blockchain layer. Okay, so each block, it not just the value of the previous block, it also contains a digest of word value that allows us to verify that the value has not changed. That means it exhibits the property of a tamper evident log. So if an adversary, if he modifies the data at any location, he needs to modify the data at the previous locations as well. So this makes the attack even harder. Okay, so you cannot tamper the data. If you tamper the data at one place, you need to tamper the data at multiple places, at all the previous places. So the tampering will be easily detected. It will be caught, okay, at the last block. So this blockchain construction mechanism is called the Merkle-Damgard construction mechanism. Okay, so and the block at the beginning of the linked list, this is called the genesis block. That is the first block that has been created in the blockchain. That is called the genesis block. So this is the typical structure of a block. Over here, you have the transactions. So whatever financial transactions that you will be doing, okay, they are stored as the root, they are stored as the leaves of this Merkle-Damgard tree, and each of these transactions are passed through a hash function. So these nodes are basically the hash values of the corresponding transactions, and then they are again passed through a hash, okay, hash function to generate the next set of hash function, and this forms the root. So a typical block, what does it contain? It contains the hash of the previous block, that is, this is the hash pointer. It contains the TX root that stores all these transactions through these hash values that is generated randomly, and that is the time at this block 11 is generated. Okay, so this is the entire structure of how the blocks are being stored in a blockchain ledger. It is being stored as in the form of Merkle trees. So you have these hash values. So these are two hash functions over here and over here. It is being branched out, and the transactions are there as the leaf nodes. So this leaf node, okay, the hash pointer. So this hash pointer points to the location where this data is stored. This hash pointer, it points to the data at the location where it is stored, and this tree is built up from the leaf towards the root. So this type of tree is called a Merkle tree, wherein the data blocks are grouped in pairs, and the hash of each of these blocks is stored in this parent node. The parent node are in turn grouped in pairs, and their hashes are stored one level up the tree. So this is called the Merkle tree. Okay, so the proof of the membership, that is whether a data exists or not in this record, Okay, that can be checked within a very small time of the order of log. That is, where n is the number of data blocks. Okay, to prove that whether a data block is included in the tree, one only needs to show the blocks in the path from that data block to the root. So one should be able to traverse through this tree and find the data. So if there are n nodes in the tree, only about log n items need to be shown. Okay, and even if the Merkle tree contains a large number of nodes in the tree, we can still prove the membership in a relatively small time. So over here, what do we do is that we sort all this entire data sets, okay, and then find that whether a particular data is there or not by identifying its neighbor data value. So if we want to find a specific data and we identify the neighborhood data, then we can see that whether that data exists or not. If these two data values are indeed neighbors, then that means this data does not exist. Okay, so you can use this Merkle-Damgard tree to check for the presence or non-presence of any specific data record. So blockchain can be used for non-membership proof non-membership proofs, that is in the form of sorted Merkle tree, as I said. Okay, so you need to show a path to the item that is just before the item and show a path to the item that is just after it is. And if these two items are basically the children of the same parent node, that means the data that you are searching for, it does not exist in that tree. So more generally, we can use hash pointers in any pointerless data structure that has no cycles. And that means it starts at a root node and it approaches towards the leaf. That means you can apply it to any directed acyclic graphs. So you can apply this set of hash pointers to any data structures based on directed acyclic graphs. Any questions, anybody? Okay, so we'll quickly move on to the next cryptographic primitives that is used for the security in the blockchain technology, that is the digital signatures. Okay, so what is a digital signature? So digital signature is basically the digital analogy of the physical signature. So it is used to provide the authentication of the messages, the authentication of any transactions that have been performed. So over here, what you do is that whenever you authorize a certain letter or a document, you put your own signature. Okay, so the authorized user, he or she puts her own signature. Other users, they establish that whether that signature is valid or not. Okay, so it is a digital analog to the handwritten signature. So what do we want? So what are the requirements from such signature schemes? Only a particular person can sign a document, but everybody else can verify that document or verify the signature on the document. So the signature is basically is tied to a particular document, and it can't be cut and pasted to another document. So how can we build this in a digital form using cryptography? So digital signature schemes are formally stated as follows. So first, in the first step, you need to generate a key, the pair of keys. So given the input, the key size, that is what should be the key size. Okay, using the key size, you generate a pair of keys, that is a secret key and the public key. So over here, the secret key is kept privately, and this secret key is used to sign the messages because only that user should be able to put his or her signature, and everybody else should be able to validate their signature, and that validation happens with the user's public key. So this is first step is to generate the pair of keys, that is the secret key and the public key. The second step is to sign that particular file or sign that particular message with his or her own secret key. So this act of putting the signature is called the sign function, and this is the signed document, that is SIG. SIG is basically your signed document, and then you need to verify that whether the signature is valid or not. So what do? You take the signed document, you take the public key, okay, and then you verify that whether when you decrypt it with the public key, when you decrypt this signed document with the public key, whether you get the message back or not. If you are able to get the message back, that means this is a valid signature. So it returns a bool. It either returns a true or it returns a false. So we have these characteristics: the generate keys and the sign. They can be randomized algorithm. The generate keys, when they are randomized, that is when this algorithm is randomized, then it generates different keys for each iteration for different persons. And for the verify, this should be deterministic. It should correctly say that whether a signature is valid or not. Okay, that is signature validation should not be random. Otherwise, the reliability of this entire signature scheme this may be disrupted. So security properties, that is, valid signatures must verify. So verify of this must be equal to true, and signatures are existentially unforgeable. Unforgeable means if I am putting my signatures, okay, nobody on my behalf should be able to put my signature. So that means what? That means signatures are existentially unforgeable. So an adversary who knows the public key gets to see the signatures. He can see as many signatures as possible, okay, for the target user. And after observing all these signatures, he should not be able to produce a verified signature on a new message. So this is the unforgeability game that is being played by the child between the challenger. The challenger is the one who signs the documents, and the attacker is the one who claims that this attacker can break into the challenger's signature. So this is a protocol. So this is a game that is being played. It is called the unforgeability game. So coming to the practical stuff, in digital signature schemes, the algorithms are randomized. And for this, you need a good source of randomness. That means the pseudo-random number generators that are being used to generate such random numbers, they should be efficient, okay, and they should have a high quality of randomness. They should pass a set of or a suite of randomness tests, okay, and there should be a limit on the message size. As there is a limit on the message size for the digital signature scheme, so what do you need to do? You have suppose you have an infinite message. So what do? You pass that message through a hash function, and as this hash function, it produces a fixed size output, okay, then that fixed size output is passed through this digital signature scheme. The only condition is that this hash function should be collision resistant. And in addition to collision resistant, it should satisfy additional 4 properties. So over here, the trick is that you may need to sign only a hash point. Instead of the hash, you may need to sign a hash point. So your signature, in this case, if you sign a typical hash pointer, then the signature, it covers the entire structure of the blockchain. So anywhere if any data is getting tampered, it will be easily caught up. Okay, so the typical Bitcoin, the blockchain technology so this is the most initial application of a blockchain technology, that is a Bitcoin. It uses the elliptic curve digital signature algorithm. So this algorithm is used to put signatures on the corresponding documents. So over here, what we learned is that this good randomness is essential. Okay, if your randomness is not efficient, if this randomness generation is not good, then you may end up in generating deterministic keys. So keys should be randomized. If you are able to generate, if you generate only deterministic keys, then anybody can attack your scheme. So the elliptic curve digital signature algorithm, it has now become a US government standard, and it has been analyzed over a period of years, and it has been believed to be cryptographically secure. So it adopts the standard elliptic curve SECP 256K1, and it has this following set of parameters. It takes in a private key of 256 bits, public key of 512 bits. The message that is being to be signed is partitioned into 256-bit chunk, and the signature size is basically 512 bits. So elliptic curve digital signature algorithm can only sign 256-bit long messages. So that's why even if the message is long, you split that message, you pass it through the hash function, a crypto SHA-256 hash. Okay, and the SHA-256 hash, it generates the 256-bit hash, which goes for signature to this elliptic curve digital signature algorithm. So in DSA, you use the public keys as an identity of a person in the system over here, and it uses and it can be used to create a new identity called the generating keys function. Okay, so here is an example of generating a Bitcoin. So here, so we have the coin. We generate a coin first, okay, that has never been generated before, and then a string is constructed using that coin ID, that is this create coin function, and then whenever you generate this coin or the string, you need to sign, okay, whenever you see a note, okay, the RBI signs on it. So similarly, when you create a coin, you need to sign your coin by using your secret key. So over here, this coin, what does a coin comprise? It comprises of the actual coin along with the generator's signature. So this gives into the coin, and anybody can verify the signature using the generator's valid signature. And from rule 2, whenever you are transferring a coin, this transferring of a coin is done through a set of cryptographic and a set of cryptographic operations. Okay, so this is a typical example. You use this hash pointer that refers to that points to the point. You use the Alice's public key to encrypt it. Okay, and then he has to sign as many transactions as possible to spend that coin. And once this data structure representing rupees transaction signed by him exists, Alice owns the coin. So this is the entire flowchart where we see a typical example when a user Alice wants to buy an item from Bob. In that case, Alice needs to make a payment to Bob. So what does Alice do? Alice first creates a coin, okay, using cryptographic signatures, using the cryptographic hash and digital signature scheme. And then when Alice is passing that coin on to Bob, she provides she runs another set of cryptographic schemes. Okay, so Alice again needs to sign that coin whenever she passes on to that coin, so that it creates a timestamp of when the financial transaction was being done. Okay, so at each step, whenever a transaction is being done, it is verified at each step. So all the signatures, okay, they are being verified. The hashes are being run to establish the data integrity check. So this is a typical toy example. So there are certain rules of using such for using such coin transaction. So you can see it in the slides over here. Again, coming back to the original flowchart over here. So whenever a coin goes from user 1 to user 2, okay, the user 1 must put his or her own signature, and that signature is being done using the private key of that user. And when that coin goes to the recipient, he verifies with the owner's public key. Okay, he verifies with the owner's public key, and then he signs that coin again when he passes on that coin to another user. Okay, so for signing, you use your private key, and for validating that signature, you use the public key. So this is another such example. You can take a look at it on the slide. So I stop my slide presentation over here. Any questions? Anybody? Anybody wants to ask? Okay, so I stop over here. Thank you.
लेफ्ट नहीं केली मॅडम दिसत आहे
It has been such an honor to be a part of this wonderful session. On behalf of the organization, I would like to extend my heartfelt gratitude to our guest, Dr. Bodhisatwa Mazumdar sir, for this faculty development program on security aspects of blockchain technology. Thank you so much, sir. Sincere thanks to the head of the departments to conduct this session. Finally, I would like to thank all of you present here for making the time to be with us today. Thank you once again. And all the participants are kindly requested to join the session at 2:30 p.m. for valedictory session.